Our last presentation is entitled Application of Cathodic Protection to Mitigate Corrosion and Rehabilitate Bridges. Chris Ball will be doing this presentation. Chris is president of Vector Corrosion Services, is based in Tampa, Florida.
And my objective is to effectively cover off a range of different options of different types of cathodic protection that could be used for different types of applications. There's a few pictures that I've taken in different locations through the years. I think it's always interesting to see the problems that we face. You know, the picture in the upper left is a bridge beam. These are in different states and unnamed states in the northeast, where you have a beam that's been repaired. You see some embedded welded wire mesh, so that's likely a shotcrete repair that's continued to corrode. And then, you know, you have a series of deck patches through the years, and you can see a patchwork quilt of repairs and some more areas that have been marked out for future repairs. And then another type of project that I've seen as well is, you know, this is a beam on a bridge, and obviously by looking at it, you have a surface barrier protection, a coating system that's been placed on top of the beam, but you have a concrete spall that's occurred beneath that, and so you had ongoing corrosion that continued to occur beneath the coating. So all of these are different types of repair systems that are probably not meeting the longevity of the rehabilitation that was originally desired. Many of you have probably seen this book. It was published by the Federal Highway Administration. I think it's not published now anymore, but I think you can get it electronically. If you're interested, there is the publication number. But it gives you some of the background information about the cost of corrosion. You guys can read the slide as well as I could read it to you. But you know, I think if you look at all the statistics, you know, there's definitely a place for repair, rehabilitation, or to try to prevent getting to the point where we need to replace infrastructure. In this guide, it lists the different options that are available for preventive maintenance activities, and I just selected a few out of the guide that were specifically mentioned with regard to corrosion protection systems. And so you have cathodic protection, and we've heard a lot about that, particularly in the previous speaker. It can be used on decks, superstructures, etc. It can be used with or without concrete repairs. There's electrochemical chloride extraction systems. There's also cathodic protection jackets as well. And you know, within these, there's different types of systems. There's galvanic systems, there's impressed current systems, there's the electrochemical treatments, and then the future developments, like Ali was just talking about with regard to hybrid type options. So these are mentioned in the guide. So what I'll do is kind of go through and cover some applications for each of those types of systems. One thing I just wanted to point out, though, that from a bridge preservation standpoint, you know, obviously there's a lot of discussion and modeling about, you know, service life. So there's a financial aspect that's important, and you can demonstrate that you can save economic resources with bridge preservation. But there's also, you know, preservation also preserves natural resources as well. And I just pulled a couple of statistics from a report from the World Economic Forum about the construction industry as being almost 50% of the total use of natural resources. I think that was kind of specific to the U.S. And that up to 40% of solid waste comes from construction and demolition. So, you know, in addition to the economic resources, there's other benefits that we can promote as bridge preservation professionals to extend the life of structures. So when we talk about galvanic protection, what is galvanic protection? We had a presentation earlier about zinc, hot dip zinc and metallizing. But effectively, galvanic protection is when you're using the electrochemical potential of two different metals to provide an electrical current between the metals. So in the case of concrete, reinforced concrete, we're typically using a zinc which has a much more electronegative or higher potential for corrosion. It's connected to the reinforcing steel, And you see a typical range of potentials potentially for reinforcing steel. So for example, if you have potentially a 500 millivolt potential and at the steel you may have 500 or 600 millivolts of driving potential to provide this electrical current. So you have the electrical path for the electron flow, but you also have an ionic flow through the concrete. So the more moisture that you have in the concrete, the more conductive, the more current will flow between the two metals. So over time, the zinc is giving electrons off, it's corroding, it's reducing its metallic mass, and that current is used to protect the reinforcing steel. One thing you might find interesting, there is a guide. The first types of system we'll talk about briefly are embedded galvanic anodes. ACI has a guide for installation of embedded galvanic anodes. It's a free download from ACI if you're interested. But within that guideline, it kind of defines embedded galvanic anodes as type 1 anodes, which are used for concrete repair and generally are considered cathodic prevention anodes. You have type 2 anodes, which are installed into sound concrete as more of a proactive preventative for corrosion control. And there are also different types of activation methods for galvanic anodes, either alkali activated or sometimes using halide salts. So, our first line of defense is to do the concrete repairs. This is another excellent educational document. If you don't have it, I would get it. It's from the International Concrete Repair Institute. It's about just proper procedures for doing repairs of chloride or corrosion damaged concrete. And if we follow these procedures, we're going to do a really good job of repairing the concrete, but also providing corrosion protection within the repair itself. Chipping behind the bar, cleaning the steel, saw cut edges, rectangular or square shapes, and also surface cleaning. But one thing in this guide, it also talks about to improve the durability is if you can expand the area of repair to get outside of just of the deteriorated area and move into clean steel around the edges. That's another way that the repair itself can encapsulate the entire corroding area or the anodic area. So in many cases, you're leaving behind chloride contaminated concrete, even if you follow good concrete repair procedures like we saw with ICRI. So in this case, these are an application potentially where you can look at using embedded galvanic anodes. In this case, this is just an illustration of a type 1 embedded galvanic anode connected to the reinforcing steel at the edge of a concrete patch repair. And the idea is just to provide localized protection. It's not solving all of your corrosion problems. It's really just there to designed to extend the life of the repairs to prevent, if we can, new corrosion activity from occurring around the edge of the patch where you still have chloride contaminated concrete. So just a photograph of a bridge structure that uses a type 1A embedded galvanic anode, localized concrete repair, galvanic anodes attached to the steel and the concrete replaced. And so the idea is that for this area, we want to make that repair last as long as we can. But these types of anodes are also used not only for concrete repairs, but in some cases for cathodic prevention or corrosion prevention. You may have situations where you have joints that are created that you may want to, and we saw a presentation from earlier today from Brian Pales about corrosion activity occurring at cracks in construction joints. So in this case, this is a bridge widening project where you may or may not have really active corrosion at this point, but you're leaving a construction joint in place, and you can see some anodes just placed right at that interface between the new and old section. In some cases, you can move to larger anodes for the construction joints using more distributed anodes. This is a similar situation where you have the replacement of a parapet wall, and in this case, you're leaving the existing bars, the stirrups that are coming up out of the slab, but replacing the parapet, so you have this interface between the old contaminated concrete and then a new concrete section that's being placed for the wall. And just to provide a localized, targeted area of protection right there is an economical use of this type of system. You could do the same thing for if you're replacing, potentially if you're replacing joints and making decks continuous, those types of applications. Hydro-demolition If you have hydro-demolition, you're going to a barrier edge, and you're leaving that joint, that's more of a targeted type of application. Just going back to show a little bit of information about the embedded type 1A anodes. 15 years of service, some anodes were pulled out of the structure and kind of forensically looked at, and you see the zinc core, which is corroded over time. The zinc corrosion products are moving into the surrounding alkali mortar, and just being able to measure the amount of current over time that's coming off the anodes. And these were measured to be within the band for cathodic prevention as defined by the European standard, which is 0.2 to 2 milliamps per square meter. And so by taking these out and physically measuring the service life, it's estimated 25, 35 years based upon this certain installation. That's probably a little bit higher than a lot of other places, to be honest with you, but that was based upon some forensics. Another installation for Type 2. Type 2 are these types of systems are installed into drilled holes. This is a project that was in New York State, upstate. They didn't want to close down the bridge, long detours. They were kind of a rural area. They had drainage, improper drainage, and the only corrosion problem on the structure was really just on the outside box beam only. So they wanted to extend the life of that specific beam in order to delay the replacement of the beam to the future, which was replaced about 10 years later. So in that case, they looked at using the Type 2 corrosion control anode placed along the outside face where the drainage was, and then one underneath as well. And you see the kind of the pattern of the galvanic anodes, the interconnecting header wire. You know, some of the anodes were placed in sound concrete, some of them went through the repair areas, but two continuous rows across the face. And then the shotcrete repair was completed, and that stayed in place until a later time when they had the capability to replace the beam. So kind of a targeted protection to a specific area. If you want to go to higher level protection, moving from corrosion control more into cathodic protection, you need larger anodes. You're generally looking at larger areas of protections. And this is some deck repair and overlays where you see these green strips are long galvanic anodes. They're placed in the repair area, and then in some areas were cut into slots where you had sound concrete. Then the concrete was placed back, and then you had a membrane and asphalt placed on top. And you know, based on the amount of anodes placed there, you're achieving full cathodic protection of the deck. And these can be designed for longer life. You can also use those types of anodes just for column jacketing and concrete jacketing. This is a new cage of steel placed around an existing column with anodes placed within. One other thing here with regard to distributed anodes, just to show a picture of a project in Florida. And these are basically columns that are out of the water. So these are being used as embedded anodes within jackets. Florida DOT has done a couple of these types of projects. This is FRP form within the anodes embedded within the encasement. You can also, in some cases, look at PVC forms. This is some data from Florida DOT. This project was installed in 2012, so it's 4.5 years old. And if you understand the corrosion testing, you know, it's getting high levels of polarization and current. The same type of situation with regard to abutment walls, abutment wall repairs. This is Ohio DOT, slab bridges, joints over the abutment wall, spalling. You know, they used to replace the slabs, but that would cause a lot of issues. So the face was expanded, and then distributed anodes are placed within the expanded, basically a wall in front of a wall. And you see the anodes placed here. New reinforcing steel is placed, the form was placed, self-consolidating concrete was used to build out the wall, and that was monitored. That was in 2005, and those are continuing to perform very well. This is 10-year data on that. We saw a little bit about metallizing. Metallizing is also used on concrete for cathodic protection purposes. This is kind of showing a zinc metallizing option. This is a project in Ontario where they did a corrosion investigation. You saw, not everything's corroding in a similar way. You had some areas that had more contamination, higher corrosion potentials, and some kind of variation there. So the DOT basically came out with a kind of a system where you have, in some cases it was just lower levels of damage, they did concrete repairs, and higher areas, or lower levels of damage but higher corrosion potentials, they did passive cathodic protection, and that was with the metallizing system. So just like you saw in the steel bridge, this is a metallizing unit. You have 2 wires of zinc that comes through the unit. They're energized, they arc across at the center, and the molten zinc's blown onto the concrete surface and connected to the reinforcing steel to provide galvanic protection. And you see the work in progress here. In this case, they used a humectant to increase the moisture at the anode for higher current. Compressed current cathodic protection, we saw that earlier. This is just an example of cathodic protection. There's been a lot of discussion about that. Compressed current systems, you give you a high level of control. You use typically an external power supply, a transformer rectifier, and in this case you're seeing a mixed metal oxide titanium mesh. It's basically, there's a voltage difference put onto that relative to the reinforcing steel. We want the mesh to be the anode and all the steel to be cathode, so it's protected. And as we saw earlier, monitoring and maintenance is required. If you have the lightning strikes, the system's not working, it's not functional. So that's a commitment that you need to make to these types of systems. There's mixed metal oxide mesh that's used for shotcrete repairs for vertical service. This is a Florida DOT project where you have the mesh anode that's placed on a pile cap with new reinforcing steel, and that's encased to build out the pile cap, and it has an embedded compressed current cathodic protection system. You can also, as we saw earlier, use titanium anodes within the pile caps and other structures like that, cut into slots. And this is just an example of a project that was done a couple years ago in West Virginia, I-64. The original structure, it's a viaduct that was built in 1975. It had an compressed current system installed in 1985. You see the size, it's a fairly large structure right on a major highway. The original compressed current system was a slotted system with carbon fill. They were happy with the extension of the service life, but it was time to replace the system. So they went to a more modern system in this case where you had hydro-demolition, and then after you prepared the surface, you see the titanium mesh rolls being laid out on the surface, and then that's all hooked up to the electrical system with the concrete overlay over top. And then you see underneath the bridge the wiring and the rectifier, and also remote monitoring. Electrochemical chloride extraction is similar to compressed current, except it's a temporary treatment, so you're putting a lot of current, similar like we just showed with compressed current systems, to the steel, but only for a short duration. So the idea is to passivate the steel. This is an example, and you see this used commonly on historic structures because it's a treatment that you can do. You can passivate the steel, pull the system off, and not really change the appearance of the structure too much. So this is a project that was done a few years ago back in Kansas City. It's a historic bridge. It was built in 1915. Like I said, the temporary system, you're using a temporary anode mesh. You're basically putting a temporary electrolyte to make ionic contact to the concrete. You're going to keep that moist, and then you're going to power the system for, in this case, 60-day treatment. It reduces the amount of chlorides. It generates a lot of alkalinity at the reinforcing steel. You take the system off. The structure is passive, and then you can clean it, and then you can put sealers or coatings or other things to protect the structure from being recontaminated in the future. And then we heard a little mention about hybrid systems. This is and Ali mentioned this as well. Basically, this is a Type 2 embedded anode system. It's put into sound concrete, but it has an inbuilt power supply, compressed current phase. So it's a two-stage anode. You get passivation from the initial, it's like the chloride extraction process. You want to put enough current to the steel to passivate the steel. And then after that happens, it automatically switches from an impressed current phase to a galvanic cathodic prevention phase. So it becomes more of a maintenance-free option. That happens automatically. You don't have to turn the system on, have a rectifier, then come back at a different time. So from a construction standpoint, it might be something to look at. This just gives you an idea of how this works. You have basically the active corrosion that it's occurring. We've heard a lot about that this week. The stage 1 is the electrochemical treatment phase. So that's the passivation phase. And the idea is that you're pushing the chloride away from the bar, but you're also generating hydroxyl ion at the bar, OH, which is increasing the alkalinity, lowering the chloride content, just around the bar, in order to passivate the steel. Now, the amount of current that's provided in this phase is really dependent upon the amount of chloride contamination you have. So the higher chloride contamination you have to get to the passive stage, that's important information to have when these systems are being designed. But it may take, in this case, 50 days potentially. But that automatically switches over to a galvanic cathodic prevention phase, which basically is just providing enough protection to the steel to kind of hold the passive nature in place, and that'll stay and basically extend the life of the anode life could be up to 30 years in this situation. So it's like this is a newer technology, simpler installation. There's no external power supply. It's automatic switching, and you don't have to necessarily monitor the system like an impressed current system to get the longevity out of it. So I went really fast because I wanted to cover a lot of ground, but I think, based upon, there's lots of different options out there. There's localized galvanic protection, there's global galvanic protection. You have like the distributed anodes, the metallizing. There's other things I mentioned as well, or that I didn't mention that would kind of fit in these categories, like zinc sheet anodes and things. Impressed current cathodic protection definitely has its place. High level of protection and control comes with the system monitoring. And then in some cases, electrochemical treatments may have its place as well. And this project was a project that was done in 2007. It's Idaho Rainbow Bridge. It had electrochemical chloride extraction process that was done on the arches, which were contaminated.
What really occurred to me, though, is looking at this, is that we're in a cash-strapped society, unfortunately, in this business, and we're trying to do more with less. We really need informed owners, we need consultants, we need industry, we need contractors to all work to solve this problem over here. And I'm very encouraged by what I'm seeing here in general at the National Bridge Preservation Partnership, and in particular at this meeting. And the other thing is, I just want to say something about Vector, is that they have a corrosion inhibitor they didn't even talk about, which we're looking at in terms of passivating our steel tendons. So they're a good company, and we certainly have a rapport with them.
I just wanted to make the group aware, you had mentioned the FHWA Bridge Preservation Guide. That guide is in the process of being updated right now. The new guide will probably be published in the next few weeks. So, thank you.
I didn't know that. It's as we go around and talk about concrete repair education in general and just promoting good practices and corrosion protection to extend the life of structures, that's been a guide that we've talked about a lot, and it's very useful. So I'm glad to hear that that's being updated.
I was thinking about the abutment repair. You had self-consolidating or low permeability concrete in the repair where the sacrificial anodes were embedded. And I'm just wondering, with the whole idea of that low permeability concrete is to have a low moisture concrete, and then do the sacrificial anodes work adequately in that drier environment?
Yeah, for sure. In this situation, the self-consolidating concrete was not a highly densified concrete. Okay, so if you had a high silica fume content type of self-consolidating concrete, it may potentially kind of cut off some of the current from the galvanic anodes. In some cases, you could look at the same type of philosophy with impressed current systems, which may have a higher driving voltage, or you could, instead of putting the galvanic anode into the overlay, the vertical overlay, you could look at putting similar types of systems embedded into the base concrete so it gets it out of the overlay material into the structure right where you want it to be anyway. And the other thing, just to comment too, on those types of situations, you kind of have a couple options. That project was in Ohio. They use epoxy coated rebar, so they wanted to use epoxy coated rebar in the overlay to create that new cage of reinforcing. So these anodes were just protecting the base where you still had a lot of chloride contamination. But in a lot of cases, you could just tie the new steel in with the system as well. So you're providing cathodic prevention to the new steel as well as corrosion control to the embedded steel and the chloride contaminated concrete. So there's lots of different options there, but it's a good observation. Lunchtime?
I think so.
Okay, thank you guys. Appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.